Well, here we are again, and I would like you to enjoy the session today. I'm Dr. Bettina Heinz, and I will teach you some more of this exciting field of chemistry. Today we will deal with solutions. Most of the chemical reactions take place in a chemical medium, which is usually based in a liquid, so reactions usually take place in a liquid environment. So we talk about solutions, meaning a mass liquid type of solution where a solid is dissolved. But however, there are many types of solutions, not only based on liquids, but this is what we will concentrate on. And inorganic chemistry is mostly based on the solvent liquid, but the organic chemistry field uses many other solvents like hexane or benzene or toluene, whatever. So today are the topics as follows. The solution can be broken down into solvent, solute, that mix together to make the solution. Solubility is a very important property of a chemical because in some it's more soluble and in some liquids it's less soluble. This can be very important for recrystallization of chemicals that we want to purify and so forth. We have that basic rule, like dissolves like, the associative law. That means you like to be with golfers if you play golf, and so on. Solubility is determined by outside factors like temperature, pressure, concentration, agitation, etc. We will differentiate between different types of solutions, dilute, concentrated, and according to the various phases. Remember I said there are also other solutions, like the atmosphere around us is in a way a solution, a gas solution. We will talk about dilute, concentrated, saturated, supersaturated solutions. We will talk about concentration units, percent, molarity, molality, normality, the equivalent weight I will introduce quickly, and certain calculations based on molarities and dilutions. And I will also introduce in this manner, or together in conjunction with this topic, the VSEPR theory shortly. It will be more discussed in a higher chemistry level course, but I would like to sensitize you to this because it is so important in predicting three-dimensional structures of molecules or molecular ions. And with this we can determine the overall polarity to predict whether something will be soluble in water or in a non-aqueous condition. So solutions and solubility. Solubility means to be more or less dissolved into a solvent, to make a homogeneous, usually translucent, hopefully translucent solution. That means the solute in a sense becomes invisible. Like sugar water, you would never think there would be sugar in it unless you taste it, or salt water. So the chemicals dissolve without leaving a trace behind. That means something is very soluble. As I already mentioned, the solution is made up of a solute and a solvent. So solute plus solvent gives solution. The process itself is called dissolution. And we also have thermal side effects, like with every other chemical change. So the heat of dissolution is usually considered the difference between the lattice energy that holds the particles together in the solid crystalline form and the solvation energy that is a result of solvent interaction, like hydration when water molecules are concerned and solvation when other solvent molecules are concerned. That is the encapsulation of the individual ultimate particles, which are usually the molecular species, ions or atoms, whatever we might deal with. When this is not the case, we often call the solutions colloids, but I won't talk about that today. So solubility is defined as how many grams solute can be absorbed, so to speak, by 100 grams solvent. This is the overall definition, but we have other relationships or ratios like parts per million, promille, etc. Solubility is affected by a few factors that I like to mention, and that is the electrolytic strength of the solute, if it's an electrolyte. So if it dissociates easily into ions. There's also a maximum probability factor or increase in entropy, meaning disorderliness can also be a factor, which you will learn more about later on in future classes. The relative energies of the lattice strength and solvation energy, as I just discussed. The polarity of a molecular species. Remember, a polar solute will be more readily soluble by a polar solvent. A nonpolar solute will be more readily dissolved by a nonpolar solvent. So here comes in the like associates with like principle. Then, of course, temperature, which increases the particle movement according to the kinetic molecular theory, which will be discussed in the gas laws. Pressure, mechanical agitation, also surface area can make a difference. So if something is already finely powdered, it's more soluble than when we have crude chunks of the crystals. So a solution is in a sense a mixture, but the solvent is practically the more abundant chemical, and the solute the less abundant. That means larger amounts of solvent are available, and the solute is in the lesser amount. Then we talk mostly of a solution instead of a mixture, although that's very close, everything, in terminology. Molecular solubility. Molecules make crystals just like ions, but they're called then molecular crystals. So they're intermolecular forces that hold the crystal units together in an organized array or pattern, which we call the crystal lattice. Here we have our sucrose molecule in a model type arrangement that we use in class often. So it is something that you could build out of these model kits. We have a lot of oxygen here, a carbon framework, so it's what we call an organic molecule. It's a disaccharide. It's made up of two monosaccharides, fructose and glucose. So we have sucrose as a disaccharide that everybody knows. Another name for it is also saccharose. So that's our table sugar. And it has a lot of OH groups that can make hydrogen bonds with water molecules. So you see already it is made for being soluble in water. This outside surface is sort of like the skin of the molecule. The structure inside is sort of like a skeleton. So we call the surface, that's where the electron density areas have their borderline, so to speak, and we call that the van der Waals surface. That's how far the electron clouds roughly extend. So this is our little sheep lined up in a crystal lattice. And these are the sugar cubes that we get for our coffee or tea. So that's our consumer sugar, so to speak, our table sugar. And here in the bottom you see why sugar is so soluble. It gets surrounded by these water molecules. Remember, the water molecules are dipoles, so they organize around the surface of the molecule. The hydrogen atoms of the water molecule are attracted to the negative oxygens, and the negative oxygens of the water molecules are attracted to positive areas. So we call this solvation, but the specific term when water is involved is called hydration. Now, I just talked about solutions, and I want to quickly at least address other types of solution. We're mainly dealing with solid-liquid solutions, but we also have solid and gas, which we call aerosols. We have liquid-liquid solutions, where the lesser amount liquid can be mixed into a bigger amount of another liquid. And gas-gas solutions, we have solid-solid solutions, which are called alloys, which we often find in metals, of course, and gases in liquids. Like when carbon dioxide bubbles out of your soda can, then that was carbon dioxide gas dissolved in liquid water. And humidity, of course, also pertains to a solution in our atmosphere when too much water vapor and liquid water is in the surrounding environment, which can make us suffer sometimes. Here this lady has some alloys. Real gold you can't find. It would be too soft. You could probably stretch it like a rubber band. So it has to be alloyed with other metals, often silver, platinum, or copper. And now I want to tell you something about the different dilutions of a solutions, concentration states, we could say. Dilute means only a little bit of solute is dissolved. Concentrated, there are of course many stages in between, but concentrated is quite a lot, whatever that means right now. Saturated is definitely the limit. That means you cannot dissolve any more material. The solubility range has been reached for that particular chemical in that particular liquid. So anything that you want to add would precipitate, would drop out. It's no room. You know, like in concert halls, you have a limit of how many people can be in there for emergencies, so you don't get a human stampede. But here with molecules or solutes, because they can be ionic too, but let's just generalize a solute substance, we can do a trick and make what we call a supersaturated solution, because we know that temperature affects solubility. So if we heat the solution up, we can pump in more material so that everything gets dissolved, disappears practically. And then when we carefully drop the temperature, we have a very metastable situation. That means that solution is on the borderline, so it can still appear clear to you, but once you start yelling or clapping or something, then the problem occurs that stuff can precipitate. So you have to really tiptoe around it to keep it in its quasi-stable situation. Now I can compare this to an elevator that has its limit capacity, like for instance 23, and then when too many people get in, it's sort of a borderline stability state. You can be okay, but you might not be. So that's what we call quasi-stable or metastable. So that's maximum capacity here as well. Very important in chemistry, since we are dealing with so many solutions, that we have some kind of unit for determining what type of concentration we're dealing with. Most common, of course, is molarity in chemistry. In everyday life, percentage is very common. In certain areas, normality and molality are also important, like in analytical chemistry or biochemistry, molecular biology. These two concentration units are also of importance. Percentage, what does that mean? Percent. So gram solute per 100 gram solution. Now it's a little different from solubility, which was based on 100 gram solvent. So this is based on the total solution. So once you have the solute already pre-dissolved, you can fill up with solvent until both together weigh 100 grams. So this is percent, mass. Mass we often say, because solute and solution are both based on mass. We have molarity, symbolized by capital M. And that is mole solute. So we have to weigh out a mole substance, and we have to know the molar mass for that, based on a liter solution. Also, the total solute and solvent have to add up to make a liter volume. So remember, a liter is also 1,000 milliliters, so you can use the milliliters if you need in a calculation. Related to molarity is what we call normality, and I'll quickly discuss that. It's based on the equivalent weight. Equivalent is a derivative of the mole, but it also incorporates the so-called valence, depending on what is being exchanged. If only protons are exchanged in acid-base situations, then it's based on the number of protons that a mole substance can release or exchange. So that would, if the proton valence is 2, then it would be half a mole. Or we can also relate it to the number of electrons are exchanged in a redox reaction. So let's say if 5 mole electrons are exchanged, then an equivalent mass would be 1/5 of a mole. So you see, it's very similar. It just makes it easy to combine solutions in a 1-to-1 ratio. Molality is different from the rest because it's not based on the total solution. It is really something like solubility. You weigh out a mole solute, and it's based on 1 kilogram solvent. So the solvent has to be weighed out separately, and then you mix the two together. Here we see in the picture how you would prepare a molar, normal, or percentage solution, which is based on the total solution. You weigh out your solute, pre-dissolve in the solvent, then pour it in what we call a measuring flask. And it has a certain volumetric flask, it has a certain margin, so it measures only one type of specific volume. It's calibrated, and then you put in your liquid that you pre-dissolve, and then you fill up carefully with pure solvent up till you reach the margin there. The lower meniscus of the water surface should match directly the line. Then you shake carefully, and then you have exactly that particular concentration. Now with the molality, all you have to do is weigh out the solute, weigh out the solvent, pour the stuff together, and you got it. You don't need volumetric flasks. Now let's look at some calculations dealing with molarity, since that's the most common concentration unit in everyday chemistry. We have 3 calculations that we can show you here, and that is known molarity volume of a solution, unknown is the mass. So you remember the dimensional analysis method that you learned. What is given is 100 milliliters. We need to prepare, and we have here 0.5 molar, and that translates quickly into moles over liters or milliliters. So always keep in mind that big M means a ratio. Then we have the molar mass, and we can quickly find out what we need to weigh out. Now sometimes you will be asked how much water was actually added. Well, mass of solution minus mass of solute gives you the mass of the solvent. And with the help of the density, you can calculate how much water actually was added. Another interesting property or calculation is a dilution problem. And here is that beautiful ratio or equation. Molarity 1 times volume 1 equals molarity 2 times volume 2. And that allows you to figure out how much you have to add to a certain solution to change the molarity. Quickly, I'd like to go into the VSEPR theory, which explains why something is polar or not. You look at have the Lewis dot structure, look at the electron density areas that surround the central atom, and then you have maximum distance between them, and whatever alignment you come up with, that will be the structure. For instance, this would be a trigonal planar molecule. This is formaldehyde, you see. It's a trigonal planar type. So whether single or double bonds or triple bonds, it all counts as one electron density area. Lone pairs also count, but carbon does not have a lone pair here. Then you go and do the vector analysis, and the resulting vector, if there is a resultant, then that would mean the molecule is polar. So you can say formaldehyde would probably be soluble in water. Here we have water, and you all know that water is a tetrahedral type, but the actual shape is angular because 2 of the electron density areas are not linked to anything substantial or tangible. No atoms sit there, so it's pure space or energy, just electrons, so they don't make the actual structure. But they certainly force everything, the bonds, into a certain formation. Here we have a linear molecule, so that's how you apply the VSEPR theory to determine overall polarity. And here we have an overview that you can always look at it at a more leisure time. These are the different VSEPR types. You see we have linear, trigonal planar, tetrahedral in the modified forms, trigonal bipyramidal, and octahedral that you will learn more about in future classes. Just here an interesting example. Here I don't have it as an extra picture for the overhead, but here we see a structure, octahedral structure of sulfur hexafluoride, which is an octahedron, and of course to be expected non-polar. This is the filler gas for, well, tennis balls, I see. I would like to talk also about acid-base theory shortly. One can't cover everything, everything is important, but I want to get you prepared for future classes in case you want to take them. Acids and bases are very important. You all know acids like acetic acid, vinegar is an organic acid, muriatic, hydrochloric acid, toilet bowl cleaner, for instance, base, sodium hydroxide, Drano, so you have them in your household. Let me quickly review these important acid-base concepts. So these are the topics. I can't get into everything, but we'll try the best we can. Arrhenius is the most common definition for acid bases. Acids are proton or hydrogen ion donors, and bases are hydroxide ion donors. Together they come and neutralize to water. Then we have the very important theory, Bronsted-Lowry. So acids here are also proton donors, but bases are only considered to be proton acceptors. So everything is only based on plus minus protons, or the exchange of protons. So the ammonium ion could be considered an acid because it can deliver a proton, and the conjugate base would be ammonia. So we call these a conjugate acid-base pair. They're only differentiated by a proton. So it's a very abstract way of looking at acids and bases, also very commonly in use in everyday chemistry. A little bit more exotic is the Lewis concept. And here everything boils back down to electrons. So any species that can donate an electron pair is considered a Lewis base. Anything that has an electron pair gap in its structure and would love electron pairs is called a Lewis acids. So you see here these little equations, like the lone pair on the ammonia is attracted to the proton. So that is then the Lewis base, and the proton is the Lewis acid. And together they make the ammonium ion. Or chloride would act as a Lewis base for aluminum trichloride and make aluminum tetrachloro, the chloro anion. And you see this reaction, or this aluminum chloride or trichloride as it's often said also, is a Lewis acid. Very valuable for organic synthetic reactions. And of course water would also be here considered in this reaction as a proton acceptor to make the so-called hydronium ions, which are the actual acidic ions that taste sour on our tongue. These are the actual acid carriers, but this would also be an acid-base reaction. Here we have Bronsted and Lowry, Danish and English scientists, usually physical chemists. And here we have Arrhenius, Svante August from Sweden, and Lewis, one of the most famous American chemists. And last not least, I will just cover a little bit of titration, because that's so important to find an unknown concentration with the help of a known concentration. So we need certain types of equipment, like a burette, a volumetric flask. We have already seen this, volumetric pipette. So everything is quantitatively exact. We need an indicator, which is an organic pigment that allows us to see when the neutralization has occurred, because the indicators are weak acids or bases that change their molecular environment a little bit, or electron shifts cause different absorption in the visible spectrum, and so they cause a color change. So here we have the curve of the titration. That's strong acid with strong base. You have a steep incline, and you drip your titrant, which is the known concentration, into the unknown. Then you see a color change, and then you measure and see how many milliliters you have added. And then you can do lots of calculations, which you will all learn about later on. But here we see that valuable formula again, the dilution formula, which allows us to also calculate unknown molarities. So when we dilute, the moles are unchanged. So I would like to conclude this session, and I hope you've learned enough. I can show you some molecules here quickly before we end. You see the two lone pairs of the water molecule. And with this, I'd like to say goodbye.